This is K Anand Goud, Civil Engineering Department, Institute of Aeronautical Engineering. So in this session, I am going to discuss about the assumptions which are made in the strength of materials. Okay, when you going to learn about the strength of materials, here we have to make some assumptions. So about the assumptions, we are going to discuss in this session. So coming to the introduction part of this topic, here we have one subject called engineering mechanics, right? So here it will be divided into three types now. First one is statics, and this particular mechanics of the subject will be dealt with in three stages. The first one is in statics, and next in dynamics, and next one is it is mechanics of materials. So in statics, we are not going to we are going to study about the objects when it is in rest position, right? So that is about statics. And next in dynamics, so here we are going to study about the objects when it is in motion. Okay, the acceleration will be considered in the dynamics. Okay, so without only forces will be considered, but here we are not going to consider any internal forces. Okay, the reactions will not be considered here. Okay, whatever the effect we are getting due to the application of loads, that will be not considered in this subject. But here in the mechanics of materials, we are going to deal with the stresses and strains. Okay, after application of loads, what are the stresses and strains which are developing? Okay, so that will be studied in this particular subject. And here in this session, we are going to discuss about the basic topics, basic fundamentals of the mechanics of materials here. Okay, and coming to the next one here, if you take all engineering branches, any engineering branch, it will consist of some physical systems, right? Suppose in our department in civil engineering constructions, so here we will be having some physical system, that is like buildings or else any structures, huge structures, right? That is a physical system. Okay, ultimately, suppose if you take mechanical engineering, there the machines are the physical systems, right? So when you create this physical system, directly we are not going to create, right? So we are going to create some components initially. Okay, after casting these component parts, individual component parts, by arranging these component parts, we are getting these physical systems like buildings. Okay, directly we are not going to place one building at a time, right? So by constructing one component and another component like flooring and walls, beams, columns, foundation separately, then ultimately we are getting some physical system like buildings or machines, right? So these component parts are the major part of this particular physical systems, right? So when you want to construct or else cast these component parts like individual components, then those component parts will be made up of by these materials, individual materials. Okay, so by using these materials, we are going to cast these component parts in individual component parts, and by arranging these components in particular manner, we are getting these physical systems. Okay, whatever the field. Okay, so by arranging these physical systems, we are going to apply some forces on the structures. So here the material properties are very, very important. Okay, these properties we have to study about this in this particular session. Okay, so coming to the major properties, first one is strength. Okay, what do you mean by strength here? So it is the ability of a material to resist external load against failure. Okay, so it is nothing but it is an ability of any material which is going to resist some external forces. Okay, if you apply any load on the member, it has to resist without failing. Okay, without getting any damage, without getting any cracks in the member. Okay, that has to resist the loads. Okay, that resistive force is called as a strength here. Okay, now coming to the property of material, so it is this particular strength for specific material will be constant. Okay, suppose if you take any clay material, so for that clay the strength will be constant now. Okay, whatever the source, whatever the source, the strength will be defined as same. Okay, and next here one note point, the primary design parameter is strength. Okay, whatever the design, whatever the component, whatever the structure. Okay, first we have to keep in mind that the parameter, that is strength. Okay, based upon this strength only we are going to design the object or structures. Okay, that is the first thing we have to consider while designing. Okay, next coming to the stiffness. Okay, stiffness is nothing but resistance to deformation. Okay, when you have any deformations in the member, okay, it has to resist. Okay, it should not bend that much easily. Okay, that resistance is called as a stiffness here. Okay, so if suppose this is the one of the beams, or else this is one of the columns here, and I am applying force here on this member. Okay, or else like this in this direction. So when you apply force like this, it is going to bend like this, right? So sometimes it is not going to bend. Okay, it will be in a straight form, right? So if it is in a straight form, that means it is having more stiffness. Okay, suppose if it is bending like this, then it is not having high stiffness. Okay, so this is what the stiffness means. And whenever you are going to design any structure, okay, stiffness is the secondary parameter. Okay, after considering strength, first we have to consider strength, and then we are going to consider the stiffness of the material. Okay, that means here, if the deflection is more in any material, suppose after applying the forces, if the deflection is more, that means the stiffness is less. Okay, that is the blind mark you have to remember. If the deflection is more, then the stiffness is less, and the flexibility is also very high. Okay, if the flexibility is high, then only it is going to get the deflection. That means it is having very less stiffness in the member. Okay, and next, coming to the assumptions. Okay, so while studying about the properties of materials, while designing any components in the civil engineering, we are going to make these assumptions. Okay, so assumptions are nothing but these are lies. Okay, these are not going to happen in the real situations, but without these lies we cannot go forward. Okay, so first one is, all the materials are continuous without voids and cracks. Suppose if you take any concrete material, okay, after casting this material, you will be having some voids, right? Like while placing the material, you will be getting some voids in the concrete material. But what this particular first assumption is telling, it is telling that all the materials are continuous without voids and cracks. But here in real situations, we are not getting this particular condition, right? So we will be having this voids, but we have to assume that there is no voids in the material before designing. Okay, or else there is no cracks in the material. Okay, that is what the first assumption. Okay, if you have the voids, if you consider these voids, then what is happening here? It is good. I mean, the strength will be reduced. Okay, if you have any voids or cracks, the strength will be reduced. That means here the initial values may be there if you have these voids, right? So that is why we are going to neglect these voids. Okay, so we have to assume as there is no voids in the material, or else there is no cracks in the material. Okay, and next assumption is material is homogeneous and isotropic. So here homogeneous is nothing but, here the term which is divided into two parts. Now, homo is nothing but same. Okay, it will have the same properties, and geneous is nothing but origin. Okay, homogeneous is nothing but same origin. That means the definition is at any point. Okay, if this is your component or material, at any point, just take any point in this particular object. Okay, at any point in one direction, the properties will be same. Suppose I am taking this point, and I am taking this point, and I am taking this point. So if you observe the properties in one direction, okay, only in one direction, not in all directions. Okay, not in all directions, but only in one direction. If you take any position of the material, then the properties will be same. Okay, that is what the homogeneous. One of the examples are wood material, or else iron, or else aluminum and gold. If you take wood, okay, wood will be in this form, right? Like it will be having some fibers. Okay, if you tear this wood, what is happening along this particular fiber placement only, it is going to break, right? When you cut this particular wood, it is going to break in this particular direction only. That means in this direction only the properties will be same. That is why it is breaking in this direction. Okay, suppose if you cut in this direction, horizontal direction, the force will be more. The force requirement will be more in this direction. Okay, so that is why this is one of the examples of homogeneous materials. Okay, and next, isotropic. Okay, here coming to the isotropic, it is opposite to homogeneous at one point. Okay, I'm taking this one point. At one point in any direction, properties are same. Okay, so in any direction, if you take in this direction, or else in this direction, or else in this direction, so whatever the direction, the properties will be same. Okay, that is what your isotropic materials properties. Okay, but in homogeneous, only in one direction the properties will be same, right? Okay, so here the examples are fine-grained materials like iron, gold, brass, or steel. Okay, if you apply any forces on this particular member, the properties will be same in all directions. Okay, that is what the isotropic material. And next, all homogeneous materials need not be isotropic, and vice versa. That means here, if you have any homogeneous materials, that is not called as an isotropic material, and if you have any isotropic material, that is not called as a homogeneous material. So this is the condition you have to remember. Okay, and next, homogeneous plus isotropic. That means at any point in any direction. Okay, earlier isotropic means in at one point in any direction. Okay, that is called as a isotropic material, right? So, but here homogeneous plus isotropic is nothing but at any point in any direction the properties will be same. Okay, the examples are same again, iron and gold. Okay, and next, orthographic. Okay, orthographic materials, here at one point in perpendicular direction the properties are same. That means here, if you take any layered material like marbles or mica, okay, you can observe mica in iron boxes also, like a silver material. Okay, that means the properties in perpendicular direction will be same, but in angular direction it will not be same. Okay, if you break that particular mica material or else marbles, okay, that will be broken into only in one direction, not in all directions. Okay, if you take any layered rocks, layered stones, okay, so that stone if you break, that will be broken into pieces in this direction only, in this layer wise direction only. That means in that particular horizontal direction only the properties are same. That is why it is breaking into in that direction specifically. Okay, so this is one of the examples of orthographic materials like wood, marbles, and mica. Okay, these are going to have the properties in perpendicular direction. And next, anisotropic. That means at one point in different direction. At one point in different direction, properties are different. Okay, earlier it was at one point in different directions, right? But here, at one point in different directions, different properties. That means in one direction it may break, in one direction it may have some voids. Okay, in one direction it may deflect, like you may get deflections only without getting any cracks. Okay, so this is what the anisotropic materials. Okay, so here materials with cracks and voids. One of the examples of this anisotropic materials are voids and cracks. Suppose if you have any material with voids and cracks, suppose this is your material and these are the voids which are present in the material, and here I have some cracks also like this. Okay, when you apply these forces, okay, if you have voids, it can take this load up to some loads, but if you apply the loads in this particular cracked area, then what is happening? This crack is going to extend like this into this void, and again from here it is going to extend like this. That means here properties are changing in this particular direction only. Okay, that means here when you have crack in this direction only the crack is extending, but here in this direction there is nothing changes. Okay, we are not getting any failures here. So that is why the properties will be different in different directions. Okay, at one point, if you take one point, the properties will be different in different directions. Okay, that is what the anisotropic material. Okay, and next assumption is self weight is neglected. That means when you cast any material, it will be having some weight, right? Suppose if you take a slab, okay, you are casting one slab on the walls, that slab is having some own weight, like material weight, concrete weight, or sand weight, reinforcement weight. So here, when you are going to design, when you are going to do analysis, here we are going to neglect this self weight, that is to eliminate the initial values. Okay, if you are not going to neglect the self weight, that is initially you are having some weight of the material, right? So if you neglect that weight, then we are going to start with the 0. Then the analysis will be very easy. Okay, and next, superposition principle is valid. Okay, so what is superposition principle here? So here the net effect caused by group of external forces is equals to the algebraic sum of the effects caused by each of individual loads. That means suppose this is one of the beams. Okay, so here I am applying two forces with different concentrations. Okay, and that will, what this particular principle is telling, this particular load will be equals to the effect of this particular single load. That means x plus y equal to z load I am applying here. Okay, so the effect of this individual load is some deflection, like one x deflection, right? So if you apply single force with the same concentration, then here also the effect is same as this first one. Okay, this is what the superposition principle is going to suggest. Okay, the effect of individual forces will be equals to the algebraic sum of the single force. Okay, so that is what the superposition principles. Okay, this principle is valid. Okay, sometimes it may not be valid depending upon the material, depending upon the cross section of the materials, right? But here what is telling, this principle is valid for all the materials. Okay, and next, this particular superposition principle is valid only up to proportionality limit. Okay, that means here in proportionality limit, the stress is directly proportional to strain. Okay, whenever you are having this particular condition, then up to that point, this principle is valid. Okay, that is the fourth assumption we have made during the study of this particular strength of materials. And next one, Saint Vinat's principle is valid. Like, sudden change in any parameters causes stress concentration and leads to failure. Okay, so this particular principle is suggesting that suppose when you have any member in this shape, okay, so I am applying forces like this. So here the cross section is different. Okay, right, and here the cross section is different. So when you change the cross section suddenly, okay, and that leads to the failure of this particular member at this point. Okay, suppose when you apply force here or else here, okay, so due to this sudden change in cross section, that leads to the failure of the member. Okay, that is what the Saint Vinat's principle here. Okay, so these are the different types of assumptions we have made in the study of strength of materials. Okay, the first one is all the materials are continuous without voids. Okay, so this is the first assumption. Without voids and cracks, we are going to assume we are going to assume the materials. Okay, and next one, second one is the material is homogeneous and isotropic. That means the properties are same at one point in one direction, or else at one point in all directions. Okay, that assumption we have made. That is second one. And next one is self weight is neglected. That means to eliminate the initial values of loads, we are going to neglect the self weight of the object, I mean materials. Okay, and next, superposition principle is valid. That means the effect of individual loads will be equal to the effect of single load. Okay, and that is fourth assumption. And next, Saint Vinat's principle. That means here the sudden change in any parameter causes stress concentration and leads to failure. Okay, so this will be your fifth assumption which we have made in the study of materials. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.